Anticipating some projectiles there, Mr. Bergman?
Well, you know, I've got a lot of students here today, Mr. Sams.
There are a lot of people.
Yeah, there are a lot of people around and they're taking tests.
tests.
Yeah, so I think they're somewhere mad. They're going to throw things at me.
Hey, it's entirely possible.
Yeah, so that's what I was thinking. They're going to be
Yeah.
mad at me. So, because they didn't pass their tests or
Yeah.
whatever. Yeah. So hey, vapor pressure though is an interesting topic.
It is.
I have some liquid right here, and it makes a vapor pressure.
It does. There's some gas above that. That's
Yeah,
exerting pressure.
gas. There's gas above there,
Oh, yeah.
really? Yeah, there are. Actually, you're right. And we're talking about phase diagrams too. So that's pretty cool too.
All right.
So I say we do it.
Yeah, it's going to be very conceptual. Not a whole lot of math in this topic.
Yeah,
so.
yeah. But, all right. Hey, what happened to my choo-choo train, Mr. Sams?
It's broken.
It's broken.
Yeah.
Huh. But it's way broken.
Yeah, very much so.
How did that happen?
Big, really gigantic dude stepped on it.
That's what I was thinking. It was the giant. But
Yeah,
no,
Jolly
no,
Green Giant.
Not the Jolly Green Giant. Mm-mm. Hey, it has something to do with vapor pressure.
Oh, really?
Yeah. Here's what happened.
Okay.
Think about it. Here's the choo-choo train. Woo, choo-choo-choo-choo. All right, with a little tank right here. And there was a little bit of liquid in it.
Okay.
Okay? They left the cap off.
Okay.
And it got really hot. I think it's like Houston or Dallas or some really hot place, right?
Okay.
Here, Wheels, I guess. And then somebody went and put the lid on.
Uh-huh.
And then it got cold.
It looks like it might have rained.
Yeah, then probably rained too.
Yeah.
And when it got cold, it collapsed.
Yeah, because all that vapor that was in there when it was hot, it probably turned back into a liquid.
Yeah. So that when it turns into a liquid, then there's no pressure on the inside.
Yeah.
All right, so guys, the way this works, picture here, there's all these gas particles and they're moving around. And we talked a little bit in the last podcast about what vapor pressure is. All right. So they're moving around. All of a sudden, they got
They
cold.
Yeah, it got cold and turned back into a
And then they
liquid.
turned back into a puddle of liquid, and now there's no pressure.
On
You
the-
actually create a vacuum up here,
Yeah.
and the pressure on the outside crushes this. We'll
'Cause
do a
there's-
couple of demonstrations in class
Right.
that help kind of illustrate this concept.
Right, so more pressure on the outside, less pressure on the inside.
But the pressure on the outside really didn't change.
No, it's just more than there is on the inside.
Yeah.
And it was enough the difference was enough to crush the
Crush
train
that
car.
train, really?
Oh, yeah.
Yeah, well, obviously, picture.
I've seen this done with a 50-gallon oil drum
I have
before.
too.
That is really cool.
Really, very cool. We'll
Yeah.
do this in class. You'll get to see. We thought about
Yeah.
putting it on the podcast and do a little podcast demo, but we decided
It's
you
just-
need to see this
Oh,
live.
yes, you need to see it live.
So if you're watching this on the internet, make sure your teacher does this. It's just one of the coolest
Yeah,
things.
or just look up on the internet something about like a pop can crush or something like that.
Yeah.
It'll tell you what to do with the soda can and how to make it crush.
And we'll do
similar to
that
the
in
choo-choo
class
train.
with our
Yep.
kids. Hey, and speaking of videos, we do want to make sure we understand the concept of vapor pressure. I
Yeah.
briefly talked about it that last podcast, and you were a slacker. You weren't here.
I wasn't here. Where was I? I was
were-
next door.
you
Oh,
were
that's
actually
right. I
next
had a
door.
million kids that needed
Yeah,
help.
it was one of
I
those-
was helping my students. Therefore, I'm a slacker.
Yes, that's right.
Yes.
Anyways, but let's watch this quick video clip on what vapor pressure is.
Okay.
Today I want to talk about vapor pressure. Okay, vapor pressure, as we learned, is the pressure of a gas above a liquid. So down here, I happen to have some water boiling. So as you can see, you can see steam. There is steam coming out of the top. Okay, how can we illustrate that? Well, I also have brought a yellow balloon. I like yellow. All right, I'm going to put a yellow
Isn't
balloon.
your car yellow too?
My car is yellow. Right.
Hey, look, a yellow hot plate.
A yellow hot plate. I picked the yellow hot plate.
You're gonna burn yourself.
You know, Mr. Sands, I'm going to take this and put this down here so I don't put my hand over the hot plate.
It's probably a good idea.
And I'm going to put this over the top. Ouch, ouch. Grab the guy
Or not.
with my fingers and burn my fingers. Okay. Now notice as the water boils, it is causing the balloon to expand. Why is that? That's because the gas, actually the liquid is turning to a gas and creating more pressure, and the pressure, more molecules are hitting the inside of the balloon. Pop, 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 pop. As it hits the inside of the balloon, it expands the balloon. Isn't that cool? Okay, I can illustrate that another way too. Is I have another flask right here. And this flask is filled with very hot water. You can see the steam coming out of it. And so what I'm going to do is I'm going to take the stopper, okay, the stopper, and I'm going to put the stopper into the hole.
Notice he's not jamming the thing down there. We don't want the glass to explode.
Actually, he is jamming it down there because he wants to see what's going to happen. So now what we're going to do is we're going to watch. But notice Mr. Bergman is not close. He's going to get far away because it is possible. You can see the water boiling. And so what should it do? Now I want you to think. Actually, it would be good if you paused the video for a second and predicted, oh,
Too late.
too late, there it goes. It pops the top off, right? So if you think about it here, there's gas pressure. You can see the steam coming out. Mr. Bergman burning his fingers once again. You actually can kind of see it's trying to escape. But if I jam it down just a little bit,
Just a little bit.
Mr. Bergman can't seem to get it jammed down too well, it should pop the top off here momentarily. The pressure is building up, and it pops the top off, and that's it.
Hey, what would have happened if that glassware would have had a crack or a scratch in it?
It would have exploded the glassware.
That's
Yeah.
why we always use clean glassware. And
Clean
wear safety
glassware,
glasses.
And wear safety glasses. Hey, cool. It's cool, Mr. Sam's.
Very cool.
Yeah, I like it when it pops off.
Yeah,
That's
I'm,
really
I'm
cool.
glad the flask didn't explode.
Yeah, well, it could. And
It could have.
I was pushing it pretty hard.
That's why
actually.
you had safety glasses on.
Yes, indeed, and I still do. In fact, that was
Yes, you
yesterday.
do. Why are you still wearing your safety glasses?
I
Still
still
students
have
in the room?
students in the
That's
room to
true.
throw things at me. Yeah.
Yeah, mine are
Hey,
next door.
let's talk about boiling and vapor pressure.
Okay.
Boiling point.
Yes.
What's that boiling
Well,
point?
boiling point is when the
It's like when it shakes. Shake it, shake it, shake it. No?
No.
No.
Boiling point, that's the temperature when a liquid's vapor pressure is equal to the atmospheric pressure.
Okay, so here's a very important thing. It's kind of a different thing than what you think. You think of it just going from a liquid to a gas.
Yeah, and which it does. It's the
That's
temperature
correct.
that happens. But that specific temperature occurs when, for that specific liquid, when its vapor pressure is equal to the atmospheric pressure, that's when it boils. So by heating it up, you're increasing the vapor pressure, and eventually you get it hot enough where you increase the vapor pressure to the point of the atmospheric pressure, and that's the temperature is where the boiling point
So
happens.
in that video that you just watched, we saw water boiling. And so as we saw that water boiling, the way we made it boil is we increased the temperature by putting it on the hot plate.
Right.
And what happened, of course, is the vapor pressure increased and it equaled the atmospheric pressure. There's kind of a balance between up and down,
Yep.
which causes that to occur.
All right, you keep talking. I'm going to go help some students. I'll be right back.
All right, oh yeah, the help of the student thing. What are you doing with that? So there's something called the normal boiling point, and that is the boiling point at 1 atmosphere, because boiling point is not just a function of temperature, it's also a function of the pressure. Now, 1 atmosphere is the pressure we learned at a previous last podcast, the pressure at sea level, okay, on an average day, which is 760 torr, or 1 atmosphere, which we learned about. And so what happens if you're at a different altitude? What happens to the boiling point? So, well, actually, here's the answer. This is an important graph. Make sure you copy this down, or you could print it. What happens is this is a vapor pressure chart. Vapor pressure versus temperature. And so, let's say that you live in Woodland Park, Colorado. Let's say, for the sake of argument, where the vapor pressure, or pardon me, the atmospheric pressure is roughly 575 millimeters of mercury. If you draw a line right here, you would actually draw a line down here, and you can find the boiling point of water in Woodland Park. Notice right here, this is at 760 torr. This is at 1 atmosphere. We say water boils at 100 degrees Celsius. That's true at 1 atmosphere, but it is not true in Woodland Park. In fact, water boils here at roughly about 92 degrees Celsius at 8,500 feet. And of course, that varies with temperature. In fact, hey, I think we should go on a field trip. This is a cool trip. I did this trip this summer. You'll see. And when we're talking about boiling point, we're not going to just go to Woodland Park, but my Lord, we're going to go to a very tall mountain. Here I am at the top of Mount Evans, and we've been talking about how water boils at different temperatures. Okay, Mount Evans is 14,200 feet, something like that, and the water is boiling, but I want you to notice that water is boiling at a mere 87.7 degrees Celsius. 87. Now water really boils at sea level at 100 degrees Celsius, but here we are at 14,000 feet, and because of the less pressure, there's less vapor pressure pushing on the water because of the altitude, or less air pressure, the vapor pressure can overcome the atmospheric pressure and the water can boil. That was pretty cool, Mr. Sams.
Yeah.
So it boils at a colder temperature. Now why
Yeah.
is that, Mr. Sams?
Well, the boiling point is when the vapor pressure equals the atmospheric pressure. So if you have a lower atmospheric pressure where you do at higher elevations, then the temperature that it's going to take to get your vapor pressure up to that atmospheric pressure is going to be lower.
Folks, the idea is that at the top of that mountain, the top of Mount Evans, there is less gas particles. So if you were to look at the top of a mountain and take a cube of air, what you would find, maybe let's say there's 6 air particles.
Okay.
It'd be a very small piece of air. But then if you went down at sea level,
In equal volume piece.
you might find 8 or 10.
Right, it's just more.
Actually, a better way to do it would be if we did 10. They'd say that there were, down at the bottom, there were 10. At the top of that mountain, I'm going to guess there's 7.
Right.
So you've got 30% less air, at least that mountain. If you go to the top of Mount Everest, it might be 6 or 5 even. I don't know.
Yeah.
So yeah, there's
It's
less
just-
particles.
It's less
so-
dense.
Yeah. Okay, get the idea? I think it's pretty cool. All right.
Yeah.
Now, boiling and vapor pressure. So that ultimately means that there's 2 ways that we can boil a liquid. You can either,
Increase the vapor pressure.
You can eat, oops, hello. I've got little lines. There's two things.
Yep.
Here's the little deal. Increase the temperature, which
Right,
increases the vapor
the
pressure.
vapor pressure, right.
So
Or-
actually, let's make a note there, guys. The result of this, the reason this works is this increases the vapor pressure. That's what increasing the temperature does.
Right.
Or you can lower the pressure or decrease
Right.
the pressure.
Then that would be the atmospheric pressure we're talking about there.
Yeah, lower the atmospheric pressure, which is what I did by riding my bike to the top of that mountain.
Right. Now, when you come to class, we're going to do another cool demo that you really want to see live.
Oh, my gosh.
Where we're going to lower...
The best demo of the year.
It
Mr.
is.
Sams.
It's very cool.
Yeah.
And we're going to lower the atmospheric pressure in a closed system, and it's really, really cool.
Very cool. And you have to explain it. It's
Yeah,
amazing.
It's awesome.
Because we're amazing. But actually,
Pretty much.
no, actually, because science is amazing. It's not us. The world is
Speak
itself.
for
amazing.
yourself, man.
Well, I'm amazing, but not as amazing as science. Okay,
All right.
so this is kind of saying the same thing, but let's kind of put it in terms of altitude. So the higher the altitude, the
Lower the vapor, or lower the atmospheric pressure.
lower the pressure. When I say pressure here, I'm talking about the atmospheric pressure.
Right.
Okay, the higher the altitude, the
Lower the boiling point.
lower the boiling point.
Lower atmospheric pressure.
Remember that I think it boiled at wasn't
lower-
something like 87 degrees at
Something
the
like
top
that.
of that mountain, where normally it's 100 degrees.
Right,
Woodland
at sea
Park,
level.
it's 92,
92, yeah.
93-ish, something like that. So when the vapor pressure equals the
Atmospheric pressure.
atmospheric pressure, the substance
Will boil.
boils. So that's pretty cool. Well, actually, I put words in here. I'm pretty good at that, aren't I? Well, that's good. Okay, let's talk about solids. Now, let's kind of change gears a little bit.
Okay.
Melting point. What's melting point? Tell me what the next side is. Hey guys, so we're talking about melting points. Okay, now I think you know this. I mean, this is sort of melting point.
Yeah.
So if I have a piece of ice and put it in my hand, it like melts.
Right.
So
And
it's
so
a-
that's the temperature that a substance goes from solid to liquid.
So we could draw it like this. We can say solid. This will put a little like scientific notations. Arrow. Actually, we'll do double arrow and say liquid.
Okay.
So when you go across this direction, it will melt, and actually, when you cross the other direction, it will
Freeze.
Freeze.
And that occurs at the same temperature. The melting point and the freezing point of something is the same
That is
temperature.
correct. So here is actually a pretty cool
Oh,
picture.
that's cool.
We have a guy holding some solid. What is that?
Probably gallium.
Gallium. It
Yeah.
could be mercury too.
Well, it wouldn't
Although
be. Mercury wouldn't be a solid at room temp.
Oh, that's
But
right.
ga-
Oh yeah, it'd be gallium. You're right.
Gallium will actually
right,
melt
this is
in your
gallium.
hand. Yeah.
Allium.
Yep.
Whatever.
IUM. There you
Gallium.
go.
So that's gallium, so it will melt in your hand. It's a
Yeah.
liquid, a metal. Or it's a solid, but it's just right at the boiling point. And of course, this is a classic picture. Of course, we have ice and water. I'm not sure I'd want to be walking where this guy's going. This is probably a river here, but actually, I know what the temperature of that water is, Mr. Sams. I don't even have a thermometer with me.
Really?
Yeah, you know what
What
it
is
is? It's 0 degrees Celsius because it
How do
is
you know that?
well because the water has ice in it, and all ice water is going to be 0 degrees Celsius
yeah.
because it has got substances that are solid and liquid, and so some of it's melting or freezing depending on whether it's kind of colder or getting warmer.
Yeah.
Usually, I'd guess this is probably getting warmer this time of the day year. Okay, we can also talk solids. Now, there's a funny thing called an allotrope.
Okay.
Mr. Sams, what is an allotrope?
It's when you have a solid and it's the same element, but
Same
it has
element.
a different configuration and sometimes like a different formula.
Yeah, usually like a different formula. So
Yeah.
different solid forms of the same element. So
Yeah.
a classic example is sulfur. We can have sulfur that has this 8-part
little ring.
ring.
thing, Yeah.
And so that's S8. And then there's something called white phosphorus.
Okay. Different element.
Oh, this is
Yeah, so-
white phosphorus and black phosphorus.
Right.
White phosphorus has this we call a tetrahedral
Tetrahedral.
arrangement, and this is kind of a cubic arrangement.
Right.
So there are actually two different varieties of the same
Yeah.
chemical.
So same elements, just arranged differently. Carbon.
Carbon's
we have-
pretty cool.
Yeah. So
There's several allotropes of carbon. Let's actually
Yeah.
put them all up here. Actually,
Yep.
there they are. This right here is the
That's
elemental
all-
configuration of a diamond.
Yeah, that's all tetrahedral arrangement is what we call that. Over here we've got these sheets of carbon, and then that's graphite, and so that's what's in your pencil. Now see how those sheets are kind of stacked on top of each other? They'll slide on top of each other. That's why graphite is real
Yeah.
slippery.
And also why we use it for pencil lead because it can
Yep.
slide off. And this is the kind of the most famous, well, the most recent famous one, I should say.
Called
Diamonds
a-
are pretty famous.
A buckyball.
This is called a buckyball.
Or Buckminster fullerene.
There was, why is it called Buckminster fullerene?
Because there was somebody named Buckminster Fuller who came up with it.
That's exactly right. So they named after some famous science
Yeah,
dude.
they're actually using that to deliver really, really tiny particles to spots where it couldn't normally get. It's called
what?
nanotechnology. They're
Yeah.
making also things called nanotubes. They're making something similar in a tube arrangement to deliver things,
A lot of cool
medications, and
applications
things like that.
to
Yeah.
this whole thing.
Pretty
Okay. Okay, so that's pretty cool. Some more things here. There's something called an amorphous solid. I think they're pretty cool.
Yeah, they're very
You know, we're going to do an amazing demo towards the end of the year, though, with the amorphous water. and the fish. Don't ever want to miss. It is the coolest. You know, we talked about the other demo being the coolest demo of the year. This is the
This is right up
coldest demo of the year. So
Yeah.
it's kind of cool and cold at the same time. Yeah.
Yeah.
You have to watch that. Okay. An amorphous solid is a solid when it cools down quickly and does not form a crystalline structure.
Right. We call it flash freezing. It cools really, 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 really fast.
Yeah. And so usually when a solid freezes, it forms into a crystal. But if it's cooled too quickly, it's not going to happen.
Forms into a blob.
So actually, here's the classic picture right here. Here we have a picture of some obsidian. Obsidian is volcanic glass. This substance right here, it cooled down very quickly. This was in a volcano. And when the volcanic rock cooled so quickly, it did not have a chance to form
Right.
a
Might have hit
crystal.
some water or something
Yeah.
like that and formed and froze and solidified really, really quickly
Yeah,
into
froze. That's good.
Right,
Yeah.
glass in your window it's similar. It's an amorphous solid. It doesn't have a regular shape.
Yeah. So glass is an amorphous solid. It's not a regular shape. It actually is the same consistency of silicon dioxide. Okay. So actually, we're talking about glasses, not as
Yeah.
in glasses like the safety glasses, but in glasses like for
Just different types of glass.
different kinds of glass. They are amorphous solids of silicon and oxygen. So it's good to know.
Yeah.
All right. One more topic today, Mr. Sams.
Phase diagram.
Phase diagrams are pretty cool.
I like these.
So let's talk about those phase diagrams. These are actually called tertiary phase diagrams because you have several things you're going to look at. It's a chart that shows temperatures and the pressures for a given substance. Okay? Now, there's a term we haven't defined yet.
Okay.
And that's called sublimation. Not
Yeah.
that we need to talk about this real fast. Sublimation is when a substance goes from a solid to a gas.
Yeah, and it doesn't pass through the liquid phase. It goes directly from a solid to a gas. If you've ever played with dry ice, you'll notice you have a chunk of solid, and then it just turns into vapor, and it never goes to the liquid phase. That's why it's called dry ice. It's not really ice. It's actually frozen carbon dioxide. But it's called dry because it doesn't go through the liquid phase and make things wet.
That's correct. And actually, the opposite, gas to solid, is called deposition.
Right. It gets deposited.
Deposited. Okay, here is the classic phase diagram. Let's talk about carbon dioxide. This happens to be carbon dioxide. So I want you to kind of understand what's going on in this. On this axis, on the y-axis, we have the pressure measured in pounds per square inch of carbon dioxide. And so the pounds per square inch on the Earth, I think it's 32 pounds, isn't it?
I don't know. I never really think in pounds per square
I think
inch.
pounds per square inch is 32. So right here, if I have solid carbon dioxide, and then if I were to heat it up, it will travel. This is temperature down here, of course. It's going to sublime or sublimate.
Go
we would
from
say.
the solid to the vapor.
Right, and so, but this is cool is that we have interesting, this is the solid region, this is the vapor or the gas region, and this is the liquid region, and you can see the borders between them. Now,
Right.
this is an important thing to draw a picture of, ladies
Right.
and gentlemen. Sketch it. You don't have to have all the blues and the reds and things. Okay, and so this is, they call this the vapor region, and then this the gas region. That's not really that critical. Basically, this stuff is all vapor. Now, we should talk about a very important point we call the triple point. Now, what happens at the triple point?
Then you have solids, liquids, and gases, all three present at the same time.
That's kind of cool. You can have
It's
solid,
very
liquid, and
cool.
gas at the same time. Now, we'll show you a demo with carbon dioxide
Yeah.
effects where you get to see this is very
neat.
cool.
Yep.
And there's another point called the critical point. What's the critical point?
Beyond that point, you can't have liquids, basically.
So it's always a gas beyond that
Right.
temperature.
Yep.
For carbon dioxide, that is simply about, looks like 90 degrees
Yeah.
Celsius. So if you're above 90 degrees Celsius, carbon dioxide cannot be anything but a gas.
Yeah.
All right, and then you can see a liquid. So now, this liquid vapor boundary, when you cross this boundary, what happens, Mr. Sams?
Then you're going to go from a liquid to a gas, so it's boiling,
That's boiling, and if you go across this way, it'll condense.
condensing.
And so when you cross this line, Mr. Sams, that would be...
Solid to liquid is melting.
And going across this way,
It's freezing.
freezing. And we didn't draw this line, so this is sublimating, and this is
Deposition.
deposition.
Right.
All right, pretty cool.
Yeah.
All right. Now here's the little phase diagram of water. Now this one's a little different, Mr. Sams.
Yeah.
Something is a little different. Difference, Mr. Sams, on this one. There's one line that's different.
I'm looking for it.
It is this line right here.
Oh yeah, that one goes kind of to the left.
You know, on the vapor pressure diagram of carbon dioxide, this line right here had a positive slope.
Yeah, it did.
This one here has a negative slope. So water is different. This actually explains why water is, or ice, is less dense than water, and why ice floats on water. Because its phase diagram is one of the only ones I think there might be a couple other ones. I don't know exactly what they are. I've never heard of another one, but
No.
that has a negative slope for this line.
Yeah, water's weird.
Yeah, water's a strange
But it's a good
substance.
thing.
This is
Keeps
actually a
things
good
alive.
picture. You can see the vaporization, condensation. We saw that with the callouts in the last picture. Sublimation and deposition there
Mm-hmm.
as well. So that's pretty cool. So you can see that. Now that leads to something very intriguing. Actually, here's another picture of it.
Yeah.
We should just back up. When we have 1 atmosphere, which is roughly where most people live, here in Woodland Park or maybe here. But if you were to heat up water, as I added
goes
temperature,
from a solid.
to a
to a
liquid,
liquid,
to a gas,
to a
it would
gas.
boil.
Yep.
Now I could boil the water by just having it drop down that way, couldn't I?
Right, so you could reduce the pressure instead of increasing the temperature.
That's correct. So that's pretty cool.
Yeah.
All right. Now this is actually a cool picture. Now, so if you watch the Olympics or into figure skating, something interesting happens right here as the ladies skate hits the ice. What happens to the ice?
Let's
think about
Is there
it.
another picture? Okay, yeah, let's think about it. Okay, so all of her weight, let's say, they're usually pretty small. Let's say she weighs 100 pounds.
100
All right.
pounds.
100 pounds, pushing down on that
Actually-
on that tiny, tiny, tiny little bit of her skate. That means all of her weight is being focused on that.
How about
one point.
per maybe half an inch
Yeah, probably half an inch
squared?
square.
It's a very tiny area, so that would be like,
Uh-huh.
I could do the math. You would actually divide that. You'd say there'd be 200 pounds
Per square inch.
per square inch.
Okay, that's a lot of pressure being pushed down on that ice. So we have a high pressure on that small area.
So actually, if you go back to the phase diagram, and so ice is, of course, a solid.
Right.
And if we say we're right here and we increase the pressure,
Hey, look, it goes into the
it
liquid
turns into
phase.
this stage, so it becomes a liquid. So interestingly enough, people think she's skating on ice.
No, she's
They say
skating
like Disney on ice,
No,
right?
Disney
It's actually Disney on
on
water.
water.
Because what's happening is it creates all these lines. You can see all the lines on the ice. They make small pockets of water, liquid water, and then it's easier for them to skate on the water, actually. There's ice underneath it. So that's pretty cool. All right. Hey, one last thing. I'll do the phase diagram of carbon. Hello, something just pulled up on my computer. The phase diagram of carbon is carbon. Remember we talked about the allotropes of carbon, diamonds and graphites, liquid and vapor. But interestingly enough, there's actually 2 triple points for carbon. The graphite, vapor, liquid triple point, and there's also the diamond, liquid, graphite. So how do you make a diamond? This is an interesting thing. To make a diamond, all you simply need to do is take graphite, not simply, it's not so simple as that, and you can increase the pressure. If you increase the pressure, it will turn into a diamond. And so diamonds can be manufactured, not just dug out of the ground, but manufactured. And then you make a diamond by just increasing the pressure to somewhere above 10 to the 9th pascals, which is a very high number, by the way. So very, very high pressures, you can turn graphite. So I could take something that has graphite in it, like a pencil lead, and if I apply enough pressure, I will turn it into a diamond. And so I'll make a cheap pencil and turn it into an expensive diamond. How cool would that be? That is very cool. Okay, so that in